Cell communication. Chapter 11. Cell communication. Chapter 11. First thing we need to talk about. What is communication? Okay, so talking is a form of communication, but we should not define communication as talking, because then you miss out on a whole bunch of nonverbal communication. Lydia and then Katie.
Isn't it like reception? It's like reception of signals, like transmission and reception of signals.
Transmission and reception of signals. When did we talk about this before?
The first time.
Yeah, I mean like 4 months ago, 5 months ago, and we haven't seen it since. And so communication is the transmission and the reception of signals. Katie?
I was going to say the same thing.
They're the same thing. Mark?
There are 4 ways of animal communication.
Okay. Visual, chemical, tactile,
auditory.
and auditory. So talking is just one of those 4. Talking is auditory, right? Although a lot of the times when you're having a conversation with somebody, you combine both auditory and visual. You watch their lips move and you listen to what
And
they're saying.
sometimes tactile, to use your hands.
Yeah, I mean, I don't know why you're putting your hands on somebody's face as they're talking, but I guess if you're holding hands. Well, I mean that's a little different. Yeah.
You know, like how? Okay, what if there's like a mute bird? Like, how does it survive?
A mute
Yeah.
bird that can't sing?
Yeah.
I mean, it just wouldn't be able to secure a mate. It'd have no problem surviving. In some ways, it would probably have an easier time surviving because the act of singing actually calls attention to yourself. And I don't know if you know this or not, but there are a lot of things that would love to eat a bird. And so you would have a hard time securing a mate. You would probably have to sneak copulations. It would be like the males that aren't dominant anyways, and so they'll hide out in a male's territory and try to sneak out, and they won't sing anyways, because if they did, they would alert the dominant male to their presence. Alright, so we've got our 4 types of communication. Chemical, auditory, visual, and tactile. Okay? Now, when we're talking about cellular communication, because that's what chapter 11 is, right, Trinity?
Right.
Cell communication, or cellular communication. Which of those 4 is cellular communication going to fall under? Will cells see other cells? No. Will cells hear other cells? No. Will cells touch other cells? Sometimes. And then can cells communicate chemically? Absolutely. Was that what you were going to say? So cell communication, remember again, communication is the transmission and reception of signals. Cell communication is either going to be tactile or it's going to be chemical. And sometimes it's going to be both. Sometimes it's going to be both. What might a cell communicate to another cell through tactile stimulation? Just, yeah.
DNA.
Okay, DNA is going to be involved, but later down in the process. What might one cell communicate to another cell through tactile communication? Eat me? Interesting, you're giving a specific message, which is okay. How about to communicate what type of cell you are, and to communicate how many of you are there? Okay, a lot of that is done through tactile communication. If a cell is actually physically bound to another cell, it usually can tell what type of cell it is. And that's because it's got receptors that are specific. And based on the number of cells it's attached to, it can basically get an assessment of how many cells that there are. Alright, so does that make sense? We all good on communication, what it is, and we're all good on how cells are going to communicate.
Can you say that one more time?
What communication is? Yeah, so communication is the transmission. Whoa, left off an S. Transmission and reception of signals.
Oh my god, I'm so stupid. I probably did that.
You said that loud enough that I'm pretty sure the recording picked it up. Which means
MIT.
that's somewhat eternal. That statement you just made about yourself. Okay, so communication, transmission, and reception of signals. 4 types of communication, and they are, Mark?
Receptor communication.
Yep.
Tactile.
Tactile,
Auditory,
chemical,
and
auditory, and visual. Okay? So this is something we talked about in our first couple of weeks of class, maybe our very first week of class. Although the very first week of class, I didn't push you all that hard. I was gentle. And then by the time we got to the second week, I'm like, you know what, they can handle a chapter a day. Yeah. Auditory is sound. Okay, now, of these four, which ones are going to be involved in cell communication? Tactile and chemical. Tactile and chemical. Alright. So now we need to talk about these two in a little bit more detail, how they apply to cells, and then we can talk about it in like specific signals. How long is this chapter? Is that what you said?
Color.
Oh, you need to change the color? Okay. Are we okay to blow past this? Okay. Boom, boom, boom. It's gone. It's gone. It's gone. Okay. So for tactile communication, the two cells must be in physical contact, which makes sense, right? It's tactile. Right? If they are going to communicate through tactile signals, they need to be in physical contact with one another. Oftentimes, what you see here is a protein receptor on one cell is bound to a protein ligand on the other. Okay. And this is what you're going to find almost always when you've got tactile communication between two cells or among several cells. You're going to see a protein receptor on one cell bound to a protein ligand on the other. Sorry, there's a little green spot there.
He's alive.
hello. Me?
Richard!
Long time no see.
I know, good morning again. Welcome
Thank you.
to the best part of your day.
Absolutely. That's no
Okay.
question.
Alright. Anyone see a new term here that we've never seen before? Ligand. Tactile, oh, you've seen that before.
Oh yeah.
Ligand. Put a little box around that word. I mean, maybe draw a heart around it if you want to.
That just messes up the flow.
That messes up the flow of your notes if you drew a heart around it, or the box.
No, the heart.
The box is fine?
Yeah.
Oh, okay.
Not under.
Not like the
I'm
heart.
gonna ask
You should heart it.
You can underline it, whatever.
Could you heart
So-
for us?
Could I? No. I don't have room. So a ligand, listen to this. Ligand is a term for anything bound to a receptor.
That's it.
Yeah. So a ligand is a term for anything bound by a receptor. So do you remember the term we used for the material bound and processed by an enzyme? It did start with an S because we built the ES complex. E stands for enzyme, S stands for substrate. Okay? And so the substrate, to define substrate, how would you define it? Yeah, Mark. Well, no, it's not. They're analogous. They are not synonymous. Emma. Anything bound by an enzyme. So a ligand is anything bound by a receptor. Now the ligand doesn't have to be a protein. It can be anything that that receptor is going to bind to. However, in tactile communication, it's almost always some protein on another cell surface. And so if a protein on one cell surface is bound by a receptor on another cell surface, what happens between the two cells? They're attached together and they're communicating tactilely. Tactilely? Does that work?
Sure.
Tactilely? Tactilely. But tactilely is like doing something delicate. Yeah, how about they're communicating, listen to this, listen, you ready? They're communicating through tactile communication. Yeah.
Tactic, it's definitely tactically.
No, that's fine.
Alright.
Definitely tactically.
So this right here, this is an example, this tactile communication, this is an example of local communication. Why does that make sense? Because they gotta be physically attached together, right? It's its local environment. Alright. And for tactile, you can only communicate through tactile communication locally. That makes sense, right? Okay. But what about chemical communication? Yeah. What's up? All I did was erase my notes.
I know, but I wrote tactile and chemical and wrote that stuff next to it, but it was just for tactile, it wasn't for chemical.
Yeah, I drew an arrow.
Then erase chemical.
Oh, I thought
I
it was
drew
all one thing.
No, I drew an arrow.
Yeah, but you
No,
circled both of it together.
No, see, if it was just yes, I did. But if it were just one thing, the arrow would be outside of the circle, indicating the entire circle is going with that. But the arrow, what's the term I'm looking for? The arrow originates not on the outside of the circle, but within the circle, indicating it is not the entire circle that terminates here, but only tactile. Plus, I underlined tactile and
You underlined tactile
Originate.
afterwards.
well, it's still there.
Just erase it. You have a
Okay. All right.
I'm ready to.
So now we need to talk about chemical cellular communication. All right? Chemical cellular communication. May I erase this? Okay, that term ligand, it's going to come back over and over and over again in this chapter, just like the term substrate that is analogous to this term came up over and over and over again in chapter 8, our chapter on enzymes. Okay? And again, that's always going to happen when you have a general term like this that refers to anything bound by a receptor. In the same way, substrate referred to anything that is bound by an enzyme. Enzymes are going to come up in this chapter too. You're going to love it. All right.
Okay, I'm ready.
Okay, cool. Thank you. Yeah. You have an observation? Is it about my arrow?
No.
Is it about my poor teaching skills?
No, it's not.
Is it about my facial hair?
So you'll know what it's about.
Sure.
You have like a USC shirt on Friday in a while.
You haven't seen me on a Friday in a while. Because last week you didn't see me on Friday, the week before that you didn't see me on Friday, and then I don't think you've seen me on a Friday this calendar year. Because I've worn it every single Friday. I've been rocking that thing, even in the midst of all of the chaos, and in the midst of USC having their worst recruiting class in the last 35 years. I've still been wearing it every Friday.
Yeah.
I mean, this team next year, this team next year might be like the team that Petros Papadakis was the captain of. Petros. All right. So now we need to talk about chemical. Hey, Tori. Chemical.
Okay.
Yeah, Kyle.
They're both local.
Their chemical comes in both local and long distance. And so we're going to talk about local first. Tactile can only be local, right? Which makes sense. If you think about how are you going to communicate tactily? How are you going to use tactile communication? Right, but you got to physically touch something, right? Try to get somebody's attention, like a 7-year-old.
Mom.
Because the auditory right there, like a little bee, isn't enough, so you gotta grab them and yank until they respond. Okay? But tactile communication can only be local. Chemical can be local or long distance. Okay, so for chemical, we're gonna do local first. Local. There are two forms of local chemical communication that happen in cell-to-cell communication. First one is gap junctions, and these are in animal cells, so I'm going to put animal here. Or I can just draw a picture of myself.
Yeah.
So gap junctions, or plasmodesmata in plants. It says animals, because that looks like an O, but it's an A.
Animals.
Oh, and then there should be an S. Let's go ahead and do that. So gap junctions, if it's an animal cell, plasmodesmata, if it's a plant cell, connect the cytoplasms of adjacent cells.
Just make. Oh, so they both do that.
Yeah, so there are gap junctions. So in your body, there are cells that are side by side and have gap junctions to physically connect the cytoplasms of those two cells. So if you are one cell and you want to communicate to the other cell, the beauty is that signal never has to leave across the membrane, because it can just go right through that gap junction into the other cell. You got to build those gap junctions. They're like little protein tunnels that connect the two.
Oh, that makes sense. Okay.
Like, let's say, imagine this. Imagine you've got a best friend, and you've had this best friend for years. And then you get to be in your 40s, and now you've had this best friend for decades.
Yep.
And you happen to finally get a job in the same city, and you decide to buy houses right next door to one another.
We're doing it.
Wouldn't that be awesome? And then you're like, okay, so I know you can communicate very easily with somebody even in the same house by pulling your phone. You don't want to walk upstairs, so you send them a text message.
Right? My mom Snapchats me.
But if you really, but you all know this. You all know this. It's very difficult to have a really meaningful conversation with somebody that you can't physically see.
It is.
It's challenging. So you're like, you know what? We need to figure this out. And you get tired of walking out of your house, walking next door, and into your best friend's house. So you know what you do? You do the only reasonable thing. You turn yourself into hamsters, and you tunnel over to their house, right? You build that little Yeah.
You do the other best thing, which is just ask him to come over.
Yeah, I know, but the thing
But
is,
that involves
see,
much.
Kyle, your mom would know about this. In the Midwest, this is much easier to accomplish because houses have basements. And the thing is so you can connect your houses and nobody would even know about it. Nobody would be like, dude, that's weird, because they wouldn't even know.
What if like everyone in the neighborhood just had like a shared basement?
It'd be like the trees in Avatar.
But like if you were cool with it.
Which Avatar?
The one with James Cameron as director. Okay?
So you just seal up the
Alright, so does this make sense? Shh. So one way cells can communicate locally through chemical signaling is if their cytoplasms are physically attached. They just send material right across that protein tunnel. Okay? In plants, it's called a plasmodesmata. Actually, that's plural. What is singular? Plasmodesma. It's plasmodesma is singular, plasmodesmata is plural, and then gap junctions in animal cells to physically connect the two cells. Okay? The other type, so this I mean you basically you create this signal and it's gonna end up in the neighboring cell because you're physically connected through this gap junction. The other one is called paracrine signaling. Paracrine.
That's a cool word.
signals.
And this is not local?
This is local.
Oh, this is still
Yeah, there are two forms of local.
Oh, I thought those were the two.
That's what I thought.
No, because that's different. Those are different organisms. They can't be the
Well,
two.
you said something or something, so I thought those were two different things.
I understand the confusion, but it's still disappointing.
I'm sorry.
No, it's okay. I forgive you. Paracrine signals basically are transmitted or secreted. That's a hard word, but anyways, or secreted by one cell and diffuse to the other. Okay? Secreted or transmitted by one cell and they diffuse over to the other. What's that?
The U and diffuse.
It was really low. I mean, if you could tell it's a U,
No, I couldn't.
so you can read the word even.
You knew.
Hey, have any of you ever seen those things that they'll write and they'll just keep the first and the last letter of the
Those
word
are
and
so
scramble
cool,
the
and you
rest?
can like read it.
Yeah, and it only slows you down about 5%. Yeah, Mark.
Have you ever seen like the brain trick with the New York in the spring?
The what with the New York?
It says it's like a triangle and it says New York in the spring. But
Okay.
But they add an extra the.
Oh.
But people people don't notice that extra the. They say regular New York in the spring.
Yeah, and that's why when you're editing your papers, they actually encourage you to read them backwards. Because if you read it backwards, your brain doesn't correct the mistakes, and you won't miss as many.
Also, like read what do you mean backwards?
Read the sentences backwards. You can't read a word backwards, but you read the sentences backwards. I mean, you can, but that's not gonna help you at all. But if you read the sentence backwards, you'll catch a lot more of the mistakes. Okay. Now,
Sorry, sir.
in these local chemical communications, the signal, I want you to write this, the signal never leaves the intracellular. No,
Does this pertain
let's do this.
to local communication?
The intercellular space, not intra, inter.
Is this for both tactile and chemical or just chemical?
This is for chemical.
Chemical local communication.
Yep.
So you're defining
So local chemical communication, I don't know what that
That's
is.
a cool word.
Communication, the signal never leaves the intercellular space.
Communication.
There's this space around the cells called the intercellular space. And what do you think you call the fluid in that space? Intercellular fluid. And so in local communication, the signal never leaves that space around those cells. If it's paracrine, it's emptied into that space, diffuses to neighboring cells, enters into those cells. Or it may not enter, but it's going to trigger the cell to do something. If it's using a gap junction, or if you're a plant cell, plasmodesma, it never even enters the intercellular space.
It's like a private conversation.
Yes, super private. It's an encrypted conversation that happens. Although it's recorded because there's always a signature of this communication. Alright? Does this make sense?
It's like Snapchat. So it goes away.
Okay, does this make sense? The only thing we need to talk about left before we can get to here, and this is the really good stuff, is long distance chemical signaling.
Oh, that's what I was.
Oh, so that's the other option.
Well, yeah, it's like this. We can like talk from all over there. Pretty cool.
Okay? Is this cool? Alright, let's do this. Goodbye. 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 Okay. I want you to do this. I want you to work with those around you. I want you to take about 90 seconds. I want you to come up with some signal that a cell might need to send to a cell on the complete other side of the body. Okay? So basically what I want you to do is come up with an answer to this question. When do we need long distance cell communication? Okay? 90 seconds. Starting now.
Urgent situations, electricity. They go like electricity. You know? There's a one. It could be on the left toe. It could be on the ear. Any of the toes. The ears. Head. Unfold. I think I don't have it.
45 seconds. I have to get my shirt sleeve out of the way.
The movement's pretty great. Where is she? I don't know. At least last show.
Yeah, we're just missing Ethan.
Zach Ball, Johnny, AJ, Joey,
Sotelo.
Sotelo.
Oh, that's a lot more than I thought.
There were 7. Oh, and Meadows.
And Meadows. Meadows said.
Edgar was there. But he's still playing soccer?
Yeah.
Yeah, he could come.
I mean, he has just as good a reason not to be there as you do. And neither one of you really have a great reason. But anyways. Alright. Okay, so somebody give me a scenario in which a cell in your body needs to communicate with the cell on the other side. Mark.
Okay, so let's say your friend, like he's with you.
Yeah.
He he puts a carrying hand on your shoulder.
Yes.
And you're like as soon as he really as soon as he lays that hand on your shoulder, the nerve cells immediately send a signal right up to your brain
To comfort you.
This is weighing you. I was just touched by something.
Yeah, you know, you have receptors in your skin called Paxinian corpuscles.
I love that.
That are triggered by a gentle touch, not by a rough touch. Okay. Any other ideas? Yeah, Britt.
You slice open.
You slice open anything.
Your skin.
Let's get it specific. Your skin.
Your
where?
toe.
Okay, your toe. Did you step on a nail?
You did.
Okay.
And you immediately.
Alright, everybody. Rick just stepped on a nail.
And you immediately need an abundance of white blood cells
Oh yeah.
to come to that
You
spot
sure do.
to handle the situation.
So you weren't going pain, which is good because pain is not a chemical signal. Pain is an electrical signal, which didn't make our list, but it will when we next week we'll add electrical signals to our list of 4 signal types of the visual, auditory, tactile, and chemical. We'll add electrical as well.
Yeah.
Emma.
Yeah.
I have 2 questions.
Oh yeah, so then he said that you need to recruit white blood cells, and there is a chemical signal release in response to trauma that tells white blood cells to actually come to that area. Emma.
Okay, so it's not directly pertaining to this. So
Okay, it's 2 questions
Yes.
or 2 statements?
2 questions.
Okay, everybody,
Okay.
give Emma your attention.
It's gonna be stupid. What exactly is pain? Like,
Yeah, so pain is a
Weakness leaving the body.
pain is weakness leaving the body. Pain is a neurological response to trauma. It's basically your body's way of trying to get you to avoid dangerous things. That's why you sense pain.
I don't feel
sorry.
So it's your body's way, it knows something's potentially dangerous, and so you sense it as pain, and it's very unpleasant. And so and then you learn to associate certain things as being painful, like spending an afternoon with a particular person, and then you just avoid it. Yeah.
And then my other one is like, if you bruise your toenail,
Yeah.
why does it fall off?
So usually, so if you it's not the bruise that causes it to fall off. It's the bruise and it falling off are caused by the same thing, and that's trauma. And so if your trauma separates enough of the nail from the cortex where it's actively growing, so you'll usually bruise as a result of that trauma as well. And then if you separate enough of it, you'll lose enough connections that it'll basically the cells will deteriorate more rapidly and the nail will end up falling out. Yeah. Okay, so long distance, also known as endocrine signaling. Okay? Endocrine. Yeah, so paracrine was local, endocrine is long distance. Okay. Okay. In long distance signaling, cell secretes signal. Which enters bloodstream before diffusing into the intercellular space around the target cell.
Yes, it does.
Oh yeah,
That's okay. Spelling is hard.
it is.
I feel like there shouldn't be
Okay.
definite spelling.
So in long distance or endocrine signaling,
Thank you so much.
Bless you.
a cell secretes. Wow, that should say secretes.
Spelling is so weird.
Otherwise, it has to be cells. Nobody even corrected my grammar. Where's?
What did you say?
Oh yeah.
I thought you just gave up.
I give up.
You thought I just gave up on the English language?
What you're writing, it's not good writing it down.
So cells secrete signal, which enters bloodstream before diffusing into intercellular space around the target cell. So did this signal leave the intercellular space?
Yes, it has to. It's long distance.
What's that?
Well, if it's long distance, doesn't it have to?
Yes, it has to. Because if it's local, it'll never leave the intercellular space. But this did. It entered into the bloodstream and then had to diffuse. Now, what I want you to think about is this, and then we'll take a little bit of a break. Okay? But I need you to think before you break. Okay? How focused do you think this communication is?
What do you mean by that?
I mean, just chemical communication in general. So let's use an animal analogy. What's an animal that communicates a great deal chemically? Come on, y'all know this.
Ants?
Ants absolutely communicate an enormous amount of information chemically. So do bees. Okay? And so if let's think you're an ant and you're leaving pheromones to basically create a trail that other ants can follow, then you need to think about it is how focused is this signal? It's kind of just release the signal, hope somebody finds it,
So it's
right?
like, here you go.
Or let's think about like a wolf or wolves, a wolf pack, okay? And they communicate chemically by marking the boundaries of their territory, right?
Yes.
And it's kind of just release the signal, hope for the best, okay? So it's kind of what's happening here. You release the signal, it gets into the bloodstream and it goes everywhere. And then you just hope that there's enough of it to make it to the target cell, which requires that you release a lot of this signal. Like if you've got a gland somewhere, like your thyroid gland, and it's got to release some kind of growth hormone to get all these different parts of your body going through rapid cell development and division. It's got to just release that, and it's got to release a lot of it because the signal's going to go everywhere. And then if let's say you only had one target cell for the signal, but the signal's going to go everywhere. So we've got to ensure that some cells can respond to that signal and others won't, right? Does that make sense? That's long distance signaling. Any questions, thoughts?
Why does it do it not specific? Like, why does it risk it kind of?
Because sometimes, most of the time with chemical communication, there are several different target cells all over the body.
Oh, okay.
And so you usually don't have like a very specific target cell when you're using chemical communication, because if you do, there's a more efficient means of communicating. If you have a very specific target cell, it's electrical signals. And we haven't talked about that yet, but we will probably next week. Alright? This is chapter 11. Cell communication. Alright? Any other questions? Okay, we're going to take a little bit of a break. I will give you 3 minutes. Alrighty. Okay. So we talked about sending signals locally, sending signals long distance, but now we need to talk about how does the target cell receive the signal. Okay? How does the target cell receive the signal? What does it do with the signal? And yeah, that's pretty much it. Okay. So there's a three-step process for receiving signal. Three-step process for receiving a signal. And so now we're the target cell. I know. Now we're the target cell. Okay?
Can I do for signal reception?
Sure.
Signal reception, because that's the way.
I mean, it's the same number of words.
But it sounds fancy.
Three-step process. First one is a receptor. So this is step 1. Receptor binds the ligand. And so this ligand, it is that signal, right? The signal is a ligand. Once it gets bound by a receptor, or binded by a receptor.
What is the receptor? Is it just like
Receptor.
We'll talk about the receptor in a minute.
okay?
You're like, what is the receptor? Don't you worry. We'll talk about 4 different types of receptors.
Oh, awesome. All right.
All right. Step 1. Receptor binds the ligand. Okay? Or you can say receptor binds. Don't make fun of my aunt. Receptor binds
Looks like a
the signal.
Mega.
2.
No, that's
Like a
not
curve?
Cell.
You know what I'm? You see that?
Cell transduces the signal. The cell transduces the signal. An analogous word. Now, transduces has a very specific meaning in cells, and we'll talk about that transduction pathway. But an analogous word for transduces would be translates the signal. Trinity.
Is it transduces or transduces?
Transduces the signal. And again, an analogous word is translates, but transduction has a very specific meaning in biological cells. Tori.
Do I need to like leave a space between 1 and 2? Like, are you gonna add to them or?
I'm going to teach more about them, but you can do it down below. And then just carry that 1 down.
I like that. Like indent.
And then the third one is the cell changes in response to that signal. Okay? So step 1, a receptor binds the ligand or binds the signal. Step 2, the cell transduces the signal, and again, translates is an analogous term.
So is that basically like figures out what they're saying?
Yes,
Okay.
but it's more than just that. Because it also, as part of this transduction pathway, amplifies the signal. And then step 3 is the cell changes. Okay? And we're going to talk about all 3 of these in more detail. Okay? What types of receptors are there and how do they bind? what is this transduction pathway? I'm glad you asked. We'll talk about this. And then 3, what types of things might the cell do? Okay. All right.
Break time.
So you no, it's not break time. Do you have these 3? Okay, cool. This is going away. We're gonna talk about that.
Process for 1.
Do your other teachers lecture as much as I do?
No.
Mr. Lee.
Oh my god.
Mr. Lee?
All he does is
I feel like Mr. Lee goes on rants. Yeah, he does trailing off.
Okay. Alright, well I didn't know I was gonna start this. Okay.
But you make it the most entertaining.
I'm glad. I think it's because you don't know many 300-pound redheaded people, and it's just like I'm like a clown, right? It's like going to a rodeo and watching the clowns wrestle with the bulls.
My sister went to a rodeo the other day.
Dude, rodeos are no joke.
She went to one.
You've never been to one?
I've never been.
Oh gosh, you have to go to a rodeo.
So cool.
You,
That's like her
yeah.
thing. She goes to like a 2-step country dance club.
You absolutely have to go to a rodeo.
How do you spell wrestle?
RWRESTLE. Wrestle.
Coach
Where do you
Red.
get acid from?
It's English.
Wrestle.
Doesn't need to make sense. It just needs to be understood. Okay. All right. WRESTLE. No, that's wrestle. Okay. Okay. So there are 4. Listen. There are 4 different types of receptors, and they are all proteins. Okay. So the receptor binds the signal, right? That's step 1. Look, I put the 1 here. Let's talk about this further. There are 4 of them. They are all proteins. There are 4 of them, and they are all what? Proteins.
Proteins.
Okay, first one
Proteins.
is called G, protein. Coupling receptor. A G protein coupling receptor. G protein coupling receptor. G protein coupling receptor.
This is step 1.
It's the first type of.
This is one type of receptor that can be involved in step 1. Okay, and I want to draw this one for you.
1A.
No, it's like 1 sometimes, and then there's 1 other times, and there's 1 other times, and there's 1 other times.
It's like
This is the most common. I'm going in order. Hey, I'm going in order of most common. Okay? So G protein coupling receptor. Here's Oh, I do. Yes. Absolutely. So here's the receptor.
The number of lines do not count.
You don't need the exact number of lines that I drew. Okay? So here's the receptor right here over on the left. And what is this receptor coupled to?
The
G protein coupling receptor.
hey.
So what do you think this is right here? Here's the receptor. What is this?
The G protein.
The G protein. Oh my goodness. Critical thinking. You Trinity kids, you are great at critical thinking.
Classically educated.
You absolutely are. Okay, so here's the receptor, and it is coupled with this G protein. And the G protein has an on-off switch. Okay? And so the receptor can bind all it wants. It's not going to do anything unless the G protein is on. Okay? The receptor can bind all it wants. It's not going to do anything unless this G protein is on. Okay? And so, why do you think we call it G? Have we seen anything in this class where you've got something that starts with the G that works a lot with proteins? And we know it's not glycolysis, that uses several proteins. Yeah, I'll give you a hint. It was in the Krebs cycle, and we made this so that we can make ATP. What was it? GTP. GTP. So this G protein, look at this. Look at this.
I said glucose.
GTP bound equals on. GDP bound equals what? Off. Gosh, you guys. Killing it. Killing it. Actually killing it. No G. Okay? So this G protein, it's got a GTP bound to it if it's off. And then if you phosphorylate that GDP, it becomes GTP. Because what does DP stand for? Diphosphate. What does TP stand for? Triphosphate. How many is tri? 3. How many is di? 2. Beautiful. So if it only has 2 phosphate groups attached to this guanosine, it is off. If it's get it to third, it is now on. And then when this receptor binds something, this G protein can trigger a transduction event. But we're not ready to talk about transduction just yet. Okay? Okay, so this is one version of step 1. Okay, G protein coupling receptor. Alright? You ready for the next one?
No.
Yeah.
Yes.
Always ready.
Receptor.
Grind never stops.
Receptor.
What am I?
Wow, I need an R. Tyrosine
Wait, so is this like
You didn't
option
draw 2.
B?
kinase. Because it's not 2, this is still 1.
Are you for serious?
I mean, yeah, but
Yeah, because step 1
yeah, so
was receptor binds
so
the
it's like
signal.
step 1, option B.
Yeah, but I don't want to call it. Yeah, you can look at it that way. Step 1, option B. Yeah. Okay, so the next one is receptor tyrosine kinase. This is just beautiful. Oh man. So again, you need to draw another cell membrane. And I need you to draw 2 receptors.
Looks like plants.
Don't make fun of my drawings. Okay?
I'm not kidding.
Now, on the bottom of these receptors,
They look like people's legs sticking out of the ground. People's legs?
peoples, like stick figures?
Yeah.
Oh.
What are you drawing under that?
Oh, you'll see.
The receptor.
The rest of the receptor. You have plenty of room.
They look.
Do you see those? Do you see the T's?
Yeah.
You see all the T's? Some of them it's a little crowded, but some of them you're like, man, I've seen a T before, and that looks like a T. Do you know what that T stands for? Tyrosine.
There's a T inside of the circles.
Yes.
I cannot see that.
Nobody told you had to sit that far away from the board, Trinity. There's a beautiful chair with foam sticking out that will get caught in your hair, waiting for you right up here.
Nichols or rapper?
Yeah. Okay. So look. So these receptors, they have these tyrosine residues that are down at the bottom of this receptor. Okay. And here's what happens. Look. So these are receptors. What are they going to bind?
Kinase.
No, not kinase. What's the general term for something bound by a receptor? A ligand. This is ligand. You see this? Now they both binded. Is binded? Does that work? But bound's a different meaning altogether. I think it is binded for this one because bound has a different meaning. Anyways, they are both now attached to ligand, and here's what happens. They move together. This one moves this direction, this one moves this direction, and so then we get this scenario here.
Like, oh, there's some public displays of affection happening.
Now they're attached together. No, it's inside of your cell. Nobody sees it except for the other, I guess the other proteins.
That looks like weekday watching going.
Okay, now they are physically connected together after they bound the ligand. And we've seen this word kinase before when we talked about glycolysis. What is an enzyme that ends in kinase? What is it? It phosphorylates other things. And so, look at this. Look at this. Look at this. When they're activated, look at these. What are all those P's now attached to those tyrosine residues? They're phosphate groups that they can use to phosphorylate other proteins.
Whoa!
I was going to say to phosphate other proteins, but it's to phosphorylate other proteins. And so this is a receptor tyrosine kinase because the phosphate groups are attached to a tyrosine residue, which is one of our amino acids. What are amino acids? The building blocks of proteins. Okay? And tyrosine is one of those amino acids. At the end of this, we've got a bunch of tyrosine residues that are just hungry for phosphate groups, but they don't get phosphorylated until the receptor is activated, and then now they can transduce that signal. But we're not ready to talk about transduction yet, because we're still on step 1. Okay? So we talked about G protein coupling receptors. We talked about receptor tyrosine kinases. You good? The next two are going to be simpler. Okay? I'm going to erase this.
Wait.
See, you weren't
The
good.
grind never stops. You can erase it.
Well, yeah, because I wanted to make sure you were done, and I wanted to know how much space I needed. I mean, I'm on the bottom, but it's not gonna take very long. Okay, you're good.
Okay. Permission granted. Permission to speak freely, sir. Permission denied. Okay. Alright. Oh man. Deaver's gonna be experiencing this so soon as he joins the Air Force Academy. Oh gosh. Gonna be eating his meals like this.
Decided not to go.
Gotta get that 90-degree angle every time. Did he decide not to go?
No, he's
Just
not.
kidding. I said
Oh,
he decided.
he's not going to decide not to go. I think what may happen is he might decide to play football for the Air Force Academy. That might happen once he gets there. Because then you'd see him. Almost all of their games are nationally televised. You'd see him sitting on the sidelines. You'd be like, hey, I know him. All right. The next one are ion channels.
Wait, is this 2 or 1?
This is still 1.
This is one option C.
Ion channels. Now remember, these are still receptors because step 1 is receptor binds what? Binds the ligand or binds the signal. The next one, these are ion channels. Ion channels. So here's a membrane.
That's a nice channel.
Okay, I want you to draw this. I want you to draw this. Here's a membrane. Here's our ion channel receptor. And then look, this is an arrow showing you something's happened. And notice the arrow is not outside of the circle, but there's no circle. And then it comes over to here. What is this? What is this?
circle.
No! The ligand! Ligand!
Don't tell me that it's not like a circle.
It is a circle, but it's a ligand. So here, no ligand. Here, ligand.
Whoa.
Here, the channel is closed.
What's a light?
That channel is closed. Here, what do you think the channel is? It's open. And really, it's probably better to think about this as it's not exactly closed as much as it is inactive. But anyways, that's another story for later. Okay? So no ligand, channel is closed. Yes ligand, channel is open. And what do ion channels do? Somebody remind me from our chapter on movement across membranes.
Oh,
Yeah, Rick.
don't they like It's like active transport, right? Like,
They are not pumps. Those are
oh, that's the
pumps carry out the active transport. Channels carry out what? You know it. What type of diffusion? Facilitated diffusion. So ions cannot diffuse across the plasma membrane. Why?
Too large.
They're not too large, they're too charged. You have this big old non-polar region there that hates charged materials. We call it water hating, but really it hates anything polar and charged. It's an equal opportunity hater. Okay? So it hates anything charged or polar. So ions cannot diffuse across the plasma membrane. They have to diffuse through facilitated diffusion through an ion channel. But look, it's closed. So there could be a ton of sodium here and virtually none here, and sodium wants to go into the cell. But it can't unless this channel is opened. But the cell can control it by no ligand, yes ligand. Okay? That makes sense?
Yeah.
So that's step 1, option C. Step 1, option D. This is the last one. This is an intracellular receptor. This one we keep it very general, and we just call it an intracellular receptor.
Is this number 4?
This is number 4, or letter D. I don't draw letters unless I have to, so I didn't draw those, but if you want to. Well, I had to draw those. But I didn't have to do A, B, C, and D, because I could just say, it's step 1, option. Yeah, okay. So these intracellular receptors. The other 3, where were they? We drew them on the membrane. The rest of them were all membrane proteins. These intracellular receptors, where are they? Inside the cell. Is this Latin or Greek?
Latin.
Yeah. So these are inside of the cell. These are all on the membrane. What kinds of things can get inside of the cell in order to be bound? What kinds of things can diffuse across the cell membrane without being facilitated?
Water.
Water. Non-polar, so intracellular receptors, these bind small and or non-polar ligands.
Oh. This one has words and not a picture?
I know.
I don't
What does
like
that have to
it,
do with
because there's
small?
all pictures and you're like,
Can it be big?
I mean, if you want, you could try to convey that message in a picture.
it's a lot of
Dictionary.
brain power. And then-
Bind small and or, that's or, not on.
Why don't you just do slash? Doesn't that imply and or?
No. You have to write and.
You have to write and slash or. You can't do and
Slash
or.
just means and or.
What?
What's
This is
Wait, so you want me to just write a slash there?
Wait, no, I'm
Okay, she's
doesn't it
really-
just mean and or?
It's different. Like if you're saying, like
I don't know.
this and or this, like you can
If
use
you're doing
slash.
Listen, I didn't
it's
ha-
not and or,
He's
that's
saying,
just or.
I didn't have the.
This and
Listen.
or this or this.
Listen up. I didn't have the caliber of education that you're getting, so I don't know. I don't know the answer to that question. Okay, so intracellular receptors, they bind small and or nonpolar ligands. These kinds of ligands can diffuse into the cell without the help of a protein channel. Okay, and I'm going to give you the most common example of something that is small and or nonpolar. And it's actually both. And it is a hormone. A hormone. A hormone is a small lipid, like some kind of steroid. And so these will diffuse into the cell and will be man, I think it's binded. Will be,
Just look it up.
these will diffuse, listen to this, these will diffuse into the cell and engage an intracellular receptor. Okay? And so this is step 1. step one, right? The receptor is now bound to the ligand. And we saw in the G protein coupled, if that G protein is on, something cool can happen, right? And then we saw with the receptor tyrosine kinase, we've got now a whole bunch of phosphate groups on those tyrosine residues. And then here we've got a whole bunch of ions flushing into the cell. And then here, I mean, who knows what's going to happen here? All sorts of magical things. Okay? We're done with step one, and we can now talk about what? Step two. Step two. Talking about step two and step three is going to be much quicker than step one. Okay? And you need to know all of these. You need to know G protein coupled receptors, receptor tyrosine kinases, ion channel receptors, intracellular receptors. You got to know it all. You got to know it all, because we need a 100% pass rate on the AP exam. 100%. Okay? All right, this is disappearing. Step two. What is step two? Transduction. Step two is transduction. And I'm going to tell you that this basically follows one of two pathways. Okay? One of two pathways. Okay? You ready for this? The two pathways. One is a kinase cascade. Okay? So this is step two. Let me put a 2 here. 2. Cell transduces the signal. And it does it in one of two ways. Either through a kinase cascade.
That sounds really cool.
You are absolutely right.
Kinase Cascade.
All right.
Sounds like a toothpaste.
So here's what a kinase cascade looks like. Look at this. Look at this. Receptor is phosphorylated. Okay? So receptor is phosphorylated. And not ant. And phosphorylates protein 1. Okay? So receptor is phosphorylated after it binds the ligand, and it phosphorylates protein 1, which phosphorylates protein 2. Okay? Which does what?
Phosphorylates protein 3.
Phosphorylates protein 3.
Dude, this is just...
Etc. all the way until you get to the target protein. So you've got a kinase cascade. And this is really, really good stuff. A kinase cascade. The receptor is phosphorylated after binding the ligand. It phosphorylates protein 1. We even saw this in the receptor tyrosine kinase, right? It connected with the ligand. Those two subunits moved together, and they got phosphorylated, right? And yes. Everybody say yes.
Yes.
And then now they can phosphorylate protein 1, which can then phosphorylate protein 2, which can then phosphorylate protein 3, all the way down until you phosphorylate the target protein. Now, answer me this. What type of protein is protein 1? If protein 1 can phosphorylate another protein, what is protein 1? What do we call enzymes that facilitate phosphorylation reactions? kinases. So receptor 1 phosphorylates a kinase, which then phosphorylates another protein that can phosphorylate other proteins. So what is protein 2? It's a kinase, which phosphorylates protein 3. What is protein 3?
Kinase.
It's a kinase, and that's why we call this a kinase cascade.
Wow.
That makes sense.
But tell me this, are enzymes used during the reaction that they facilitate? No, they are not. They are not reactants. Meaning what? If protein 1 is an enzyme, it means it is not used up to make protein 2.
Whoa.
And what does that mean?
The energy doesn't like deplete.
Well, the energy depletes because you need an ATP molecule every time you're going to phosphorylate something. That phosphate group comes from ATP. So we need ATP every time we do this, but protein 1 is not used up. And what that means is, from one protein 1, we can make how many protein 2s?
1,
More than 1.
2.
At least 2, because this is not used up in the reaction that makes protein 2. It's an enzyme.
So why does it? Oh, I see.
Because this process activated this enzyme,
Yeah.
which will then activate this enzyme, which will then activate this enzyme, which will then activate all the way up until you get to whatever that target protein is to activate. Okay? Does that make sense?
Yeah.
But if protein 1 is not used up, it's not required. It is required to make protein 2, but not as a reactant. ATP is a reactant, and inactive protein 2 are the reactants. ADP and active protein 2 are the products, right? It makes sense? Protein 1 is not used up in that reaction, meaning as soon as it's done making one protein 2, it's available to make another one, and another one, and another one, and another one, so on and so forth. And so every step along this kinase cascade amplifies the signal. Because what you're activating is an enzyme that is not going to be used up in the reaction it facilitates. It would be akin to activating, I don't know, let's say like phosphofructokinase. Which, if you want to call it that. So you'll remember that is the enzyme that facilitates reaction 3 of glycolysis. Right? You'll remember that?
Sure, yeah.
Okay, so phosphofructokinase facilitates reaction 3, in which you take a phosphate group from ATP and you attach it to fructose 6-phosphate to make phospho 1,6. Wait, no. Fructose 1,6 bisphosphate. Okay?
That's kind of fancy.
But that enzyme, phosphofructokinase, is not consumed by that reaction. It gets to be involved in a whole nother process of glycolysis. Okay? So does this make sense? So this kinase cascade, you're just activating kinase enzyme after kinase enzyme after kinase enzyme, and every time you're making something that is not used up in the reaction, it facilitates. And instead just facilitates it, and then it can do it again. So every time you're amplifying this signal, and you're making it, you may have started with a single ligand molecule. One ligand molecule that bound that receptor, that got binded by the receptor. Okay? You started with one ligand molecule, and you end with millions of this target protein. Started with one, and end with millions. True or false? Millions is more than one.
Sure.
No, that's not false.
Well, millions.
Okay, so that's one way to carry out the transduction. The other way is through what are called secondary messengers. Secondary messengers. Okay? So in a kinase cascade, the receptor is phosphorylated, and then phosphorylates a kinase, which phosphorylates another kinase, which phosphorylates another kinase. Secondary messengers,
Is this B?
sure, if you want to do 2B. this is your receptor. Creates cyclic AMP. Cyclic AMP. Cyclic means circular or cycle-like. And so I'll show you in a minute what, because you see AMP and you're like, this must be related to ATP, right? Because ATP is triphosphate, ADP is diphosphate, AMP is monophosphate. But this cyclic here, that's a little different. Cyclic, whatever you want to call it.
It's like a unicycle.
And I need to get the spelling of this enzyme right. So receptor creates cyclic AMP using a enzyme called
Nope, he's going right all the way up on the table.
adenylyl.
Adenylyl?
Adenylyl. Adenylyl? Adenylyl. Adenylyl.
We're just out sniffing.
What was spelled out really wrong? 2 I's and 2 L's.
Adenylyl.
Is it YLYL?
Yeah.
Plica polonica. That's one of my favorite words.
Lamarcus?
It's actually 2 words. Plica polonica. It's when your
I feel
hair.
like they just get random words like
It's a fancy name for an ingrown hair, but it's where you have a whole cluster of ingrown hairs. Plica polonica. And it's a common symptom of a very heavy lice infestation.
I feel like they just like start, they
Yeah.
close their eyes and like write random words.
Okay. Okay. So the receptor might create cyclic AMP using an enzyme called adenylyl. So what is the secondary messenger here? Nope, that's the enzyme. This is the secondary messenger. And then cyclic AMP can go and trigger a whole bunch of different reactions. Yeah, so remember, this is secondary messengers. So in this one, the receptor phosphorylated a kinase, it activated a kinase. Here, it creates cyclic AMP.
Okay.
And cyclic AMP is the secondary messenger. And then it will go, listen to this, the recording's picking it up. Cyclic AMP will go and trigger a whole bunch of other processes as a secondary messenger. Like for instance, the primary messenger is the receptor. Okay? The other thing the receptor might do, so this is 2A, this is 2B, this is 2B1, this is 2B2. The receptor triggers the release of calcium ions. Okay? That's another option. With these secondary messengers, the 2 most common are the receptor creates cyclic AMP, which cyclic AMP is that secondary messenger, carries out or triggers a whole bunch of other processes, or the receptor triggers the release of calcium ions. And so what would this secondary messenger here be? Calcium ions, which can then go out and trigger a whole bunch of other processes. Alright? So this is signal transduction. One of these 2 things. Taking that ligand, and again, I told you what word is analogous to transduction. Translating it. So you take that ligand and you translate it into some target protein or some secondary messenger that will then trigger target proteins. Okay? This is transduction. Any questions?
No, sir.
Okay, we're not going to get to response. We'll get to that on Friday. You may deal with it a little bit on Wednesday, but I doubt it. We'll get to this on Friday, and then we'll just talk about fine-tuning real quick. But we're about 95% of the way through Chapter 11. Y'all did it.
Yeah.
You handled it. You're better for it, even if you don't feel better
I
for
feel
it.
better for it.
Okay.
I'm feeling better.
So in the remaining time that we have together, I need to tell you what's going to happen on Wednesday.